second talk will be given by Joseph Raskind about a runtime system for interruptible query processing.
All right, thank you. And good afternoon to everybody. So again, my name's Joe Raskind. I'm going to talk about the paper I contributed to, Runtime System for Interruptible Query Processing when Incremental Computing meets Fine-Grained Parallelism. So first, a bit of motivation. All of us right now, we have either laptops with us or mobile devices or things of that nature where these things are connected to the internet, and quite frequently we're constantly pinging a variety of different websites or things of that nature where we need to grab information that is kept on data servers that then have to process these queries, right? So applications and runtime systems that have to deal with a variety of different workloads that deal with and handle and process these different queries and requests that we have. And there's really no way to know a priori exactly when there's going to be large increases in the amount of queries or the types of queries that are going to come in, right? So if that's the case then, and we're interested in providing good quality of service to customers or consumers and users of these different online systems, then we need to have some sort of runtime environment that's capable of handling and dealing with these workload fluctuations. And particularly here, what we're concerned with or interested in is graph databases. So something that's become much more popular nowadays, a means of collecting data using vertices and edges. Very frequently now popular with social media data, or a lot of relations between this information. And if you're then interested in creating these runtime systems, then normally the state-of-the-art way that you're going to deal with them and process these queries is through what's called monolithic processing. And the idea is it's intuitive, it's simple, and it works. The idea is that you get a query and you just start running it until it's over, right? You run it to completion. And at no point are you interrupting that query, starting and stopping it, anything like that, right? Other than everybody here knows that maybe the system itself, the application might stop, there's some kind of OS interrupt, but the actual application, the query process is going to start and finish uninterrupted. There's also ways of speeding this up, normally through what's called batching, where you take a bunch of these operations, group them together, but still the overall philosophy is the same. You still take that batch, you start working on it, and then eventually you have to finish it without stopping at any point. Okay. So again, if we have this little toy graph, right, the 3 nodes, if I want to get to the 3rd node, I have to start from the beginning and work my way all the way to the end, never stopping. Okay. Now, what we wanted to provide in this paper is an alternative to that, a different kind of query language runtime design, which is capable of utilizing the philosophy of incremental computing and then being able to leverage that by providing fine-grained concurrency to processing queries. So the idea here is that instead of having to start a query and then run it to completion, wait for it to finish, we can start interrupting them and leveraging, getting full CPU utilization by stopping and starting these different operations. Okay? All the while, we're able to maintain sequential consistency, which is non-trivial when you consider the fact that for Pitstop, we have a dynamic system that's capable of providing for both reads and writes. So it's not just for static data. We evaluate the system using real-world data sets, which I'll talk about a little bit more later. And we're capable of outperforming Neo4j, which is what the system is a modified version of. And through this incremental computing approach, we're capable of outperforming it. We also provide a design space exploration within the paper itself, which I'll briefly touch on a little bit later as well. So the research question here is, can incremental computing be joined with query processing? And for us, our design of Pitstop is an answer to that, right? So yes, we can utilize this design philosophy. And the way that we do that is by partitioning the graph up into different pieces. These pieces we call legs, so a collection of different nodes. Each of these nodes terminate in what we call pit stops, or the thresholds between each leg. And the idea here is that we can incrementally process our queries through these different legs at these different pit stops, and deciding whether or not to continue on or batch operations together when doing so. So first, I'm going to provide sort of a little toy database here, which is 6 nodes. This is something we show in the paper as well. Nodes K through 6 here. The black solid lines indicate the logical connections between the nodes, the edges, and the dotted lines indicate the traversal path. Okay. Each of these, we're going to provide a set of queries here, so L1 through L3. L1 and L2 are reads, the standard queries for K6 and K3, and then L3 is going to be an update on K3. So first, just to provide kind of a baseline relative to what Pitstop will do, we're going to take through processing these queries using monolithic processing, so on a single core machine here. So at the first timestamp, you see indicated in red, highlighted in red in the bottom left there, the first query, L1, arrives. So at our first timestamp, L1 arrives. Then next timestamp, we can start processing L1. So pretty normal, right? Our next timestamp, we find L2 comes in, again highlighted in red. But because we're doing monolithic processing, we can't interrupt it. We can't start working on L2 or doing anything like that. We have to wait for L1 to finish. We're running it to completion. Right? So this is going to continue even when L3 shows up. Again, it's going to be waiting in a queue. We can't do anything with it. So we're just going to keep processing L1, eventually resolving that query and finishing it. That then frees up the space to start working on L2 and doing the same thing again. Right? So then we process L2, we resolve the query, then we process L3, so on and so forth, we make the update. Right? All that took about 16 of these time intervals. So now I want to show you what Pitstop would do in that same scenario. Okay, so now we have the same setup, single core machine, but now we're going to leverage the capabilities of Pitstop. So the beginning looks about the same. L1 comes in. We then start processing L1's query at that K1 node. But now L2 comes in, and we create some method of accounting for handling L2. We're still processing L1, right? But in this next timestamp, after we process through L1 in K2, we then have some space here to stop K2 at that pit stop, so to stop L1 at K2, and then allow for L2 to start processing in K1. Okay, so this is the idea of Pitstop, the idea of stopping a query and allowing for incremental propagation on other queries. Right? So then here in L3, we also stop, or at the next timestamp, we stop L2 at K1. We then process L3 at K1. And now we find that both L2 and L3 are at the same pit stop, right? So L3 is going to be processed. So we go to the next timestamp. We're capable of batching these together on the fly. So now we have L2 and L3 processed at the same time. We now find all three queries ending up at the same pit stop, so we can group them all together and then continue processing these queries. Right? So before, with monolithic processing, we weren't able to do any work with L2 or L3, but now due to this, the ability to start and stop the queries, we've now made more progress. Right? So we can keep going through here. We resolve L2 in this case, maintaining our sequential consistency so the update won't happen before the read. We keep going. Again, the decisions on what to stop and what to start will maintain that consistency, but also sort of randomly chosen on which is going to start running. Here we process L3. We keep going, finally processing L1, resolving it. And what took 16 of those time intervals before now only takes 13. So we shaved a little bit of time off. We can then further get speed up here by then throwing this into a parallel multi-threaded environment. So here with two cores, L1 comes in, we start processing it. L2 comes in, we don't have to stop L1. Processing L2 and L3 then at the same time, putting that in the same thread. We can then do the same on-the-fly batching in that thread that's dealing with L2 and L3, all the while L1 is running on its own time. All right, so we can keep moving through here, resolving those queries because they have no relation to each other. They're in two different legs, so we can be safe that there's not going to be any stepping on any toes there. Finishing it up here at time interval of 9. So we shaved off a lot of time in relation to that original monolithic processing of 16 time intervals, 13 for just using Pitstop, and 9 for then having this parallel functionality. So why does Pitstop work? How does this work? Again, it's leveraging that idea of incremental computing. So we're breaking down our propagation into finer-grained concurrency units. We're not going from end to end like in monolithic processing. This enables us to opportunistically batch on the fly, which then allows us to increase CPU utilization. We're not waiting around for anything. And what we'll see a little bit in the sort of empirical evidence is that allows us to kind of gracefully balance workloads where we get large influxes of queries in a short period of time. Yeah. Again, what's useful about Pitstop is its ability to treat reads and writes independently of each other. So as long as these reads or writes are in different legs, so different portions of the graph, we can be confident that they're not going to overwrite and provide us with unreasonable output in our query reads, which is good for performance, so we don't have to wait around on anything. Again, we can then treat those two different parallel legs, regardless on if they're reads and writes, or just reads, or both writes. We maintain sequential consistency, so queries are not serviced out of order. All that means is that if I have two queries, L1 and L2, L1 arrives before L2, then at the end of my processing of these operations, I should expect that the graph looks as if L1 was processed and then L2 was processed. Okay? So Pitstop, there's a formal proof in the supplementary materials for the paper. It's based on an operational semantics for online data processing, which is built on the Don calculus, which was published in Pitstop a few years ago. So on to the evaluation of Pitstop. We implemented Pitstop by modifying the Neo4j runtime. The machine that we ran it on was a Google Cloud VM with 96 cores and 86 gigabytes of memory, so reasonably comparable to data servers. We used real-world data sets, so a Twitter data set of 42 million users, Stack Overflow of about 12 million, and GitHub of 4.4 million. In order to mimic that idea of workload fluctuation, we released our queries using two different kind of phases. One, under-provisioned, meaning we're bombarding the system with a lot of queries, reads or writes, and an over-provisioned system where we take it a little bit slower and allow for the system to kind of recuperate if it can. Our baselines used, we have a monolithic processing baseline, which is just standard basic Neo4j, and a batch monolithic processing version where we introduced batching into the runtime, again, just grouping operations together that don't conflict with one another up to a certain threshold. And then again, those also are going to be processed from end to end. Pitstop compares very favorably to both monolithic processing and batch monolithic processing. So this is a speed up graph, so a higher number is better. This is Pitstop speed up over MP or BMP. Speed up is almost 2 orders of magnitude better in the Stack Overflow F1 situation, fluctuation. And the reason for that is because the monolithic and batch monolithic processing both have those problems with operations waiting around. Right? So we have to process things from end to end, meaning that new operations can't really have any progress being made. This is what's called the cascading effect, and it's more obviously shown in this other graph here, which is a per operation latency speed up. So what we see here is you can see these kinds of 4 quarters that the graphs are cut up in. Those are 2,500 operation quarters. Each quarter represents a new phase. So we have a UP phase, an OP, a UP, and an OP. So we're bombarding the system with a lot of operations, then taking it a little bit slower, so on and so forth. And we can see here that Pitstop has significant speed up during that UP phase because the monolithic processing and the batch monolithic processing baselines, they both have operations waiting around doing no work. So there's no chance for those operations to have any work performed on them, so they wait around, don't have anything done. This is less obvious in the smaller graphs, but in the larger graphs, there's a lot more time that those older operations have to use to pass through the larger graphs. There's also less variance in Pitstop, so because of the ability to work on multiple operations at the same time, or multiple operations, we have more of a parity between operations and their latency. Throughput is also maintained in Pitstop, so we don't sacrifice anything there. This is peak throughput. We find that even the Pitstop is capable, even in terms of peak throughput, of going beyond monolithic processing and at least being on par with or better than batch monolithic processing, so it still compares favorably. We also introduced indexing into Pitstop, meaning constant time access between our different nodes. Here, the showing that even in those situations where there's no waiting from the graph for certain operations, there's still a speed up in Pitstop. There are additional experiments in the paper where we play around with different leg sizes, so different partition sizes. We default to 1%. There are other percentages chosen. We also have ablation studies of seeing different facets of Pitstop to see if we take one thing away or not, how it performs. There's more of a discussion on that in the paper. So in conclusion, Pitstop is a novel query runtime design which is able to leverage the idea of incremental computing, which then provides it the tools to address challenging use scenarios like workload fluctuation, dealing with those times where you might have a lot of operations coming in at once and then leaving off, and dealing with long tails and the cascading effect that comes from that. Okay. So thank you, and any questions? Roads to Pitstop.
Awesome. Excellent work. I have a question about how does the memory overhead scale with using Pitstop? Because I imagine now, since you're doing multiple queries that get interrupted, that the amount of memory that has to be stored until you finish some of these goes up.
I don't have a good answer in terms of memory overhead. I don't think we provided any tests or any comparisons based on that. I mean, I'll just say that at least in terms of like additional structures that are used for Pitstop, it's not an incredible amount more, but I can't give you like solid numbers on how it compares with the default.
Okay.
Thanks, great talk. So I have a question about your methodology.
Mm-hmm.
So I had a quick read of the paper and could not really find what GC you set, because you're running a JVM, right?
Yeah.
Yeah, so you were running with the default?
It would have to, it'd be the default, yeah.
Yeah, so is it because latency is not a first-class concern, or why did you pick G1?
I don't think there was much in the way of, I guess the question, I guess I don't really know what would be the reason as to not doing that.
Yeah, so if you really care about latency, there are other GCs to choose from.
I can't
So
give a good answer as to why it was chosen.
Totally
just the defaults used.
Yeah, and another thing I could not find in the paper, are you running everything inside of the same JVM instance?
What do you mean by everything?
So like you're creating requests and responding to them. Is that happening?
Yeah, it's within the same JVM
okay,
instance.
Thanks very much.
Hey, thanks for the talk. I'm just wondering about so it seems like you batched did a little bit better than non-batched, right?
Yeah.
Like your speed up over a batch is like 5 or so, or 3.
Yeah.
I'm just wondering, why are you better than batch? Because it seems like in the example that you showed us, the first one is able to proceed because it's kind of basically unbatched.
Mm-hmm.
But then after the second and third query showed up, they're basically batched at that point.
Mm-hmm.
And at that point, it seemed like it was identical to what batch performance would be, right?
Yeah.
So I'm just wondering what the improvement of a batched.
I guess that example. Oh, sorry, but yeah, for that example, I guess it's too small to really show what the advantage is. I think in a larger graph where you have, say, 10 million possible nodes or more than that, I think also some of it has to do in terms of when those batches are coming in, because also part of Pitstop is opportunistically batching them. So you're batching things together when they're at the same leg. So then you're getting the advantage of having similar operations that can be grouped together, processed through the graph. Whereas before with the batches, you can't really rebatch things. They're all kind of in their own isolated runtimes, right? Or their own isolated processing.
Any questions? Any questions from that side of the room? Okay, thank you, Joe.
All right, thank you.